Hi everyone, this is Super CEO. It's been a long time since I've done one of these videos, but I've got one for you. Okay, so here's a little statement uh, from Cambridge. Okay, so the question that we're looking at today is this one here, question 20 of section D. So it's enrichment slash challenge question. And there's only one question, so that's either 16. It's section 16D if you've got extension 1 textbook, and it's 10D if you've got a 2-unit slash advanced textbook. Okay, so that's given. So this phi function, phi z, integrated from negative infinity to infinity is 1, which means that's a PDF, so that's given. So we're going to have to use that fact. And then you're going to have to find the EZ, the expected value of the Z, not X. So here we use Z, and Y, that expected value is 0. So we're going to have to prove that. And then you have to now differentiate this function with respect to Z, of course, and then somehow use that result to integrate this. Okay, that's my gut feeling, what my gut feeling says. And then evaluate the variance of Z. Okay. All right. So here's how we start the first one. So just rewriting what we are given with. So the integral from negative infinity to infinity of the phi function is 1, and phi, it's like a frequency function is given as that. Now, one interesting thing about this phi function is, as you notice here, the power, it's an even power, so that's an even function. Or you can, if you want to be really rigorous, then you can use f of z is equal to f of minus z, and you'll pretty much easily prove that this is an even function. Okay, so that's going to be important for this one here. So then expected value is going to be that integral of not x, but z, this is the lowercase z, times the phi function. So z times phi z, which will give you this. But then again, I can take out this coefficient outside the integral. So that's that. And now I've got this to integrate and evaluate. But here's where this evenness of this phi function comes in. Now, this is an even function, but this z is an odd function. So what's the product of odd times an even function? Well, we know that that's an odd function. Here's an example. Quick proof, not a formal proof. It's a quick proof. Just see here, y equals x, that's a typical example of an odd function. Y equals x squared is a typical example of an even function. Multiply those two, you get y equals x cubed. Then we all know that it's an odd function. So we know then for sure that this integrand is an odd function. And one of the properties of the definite integral is that when you evaluate the same um, absolute value, but different in signs, then the of integral of that odd function being the integrand is going to be 0. Okay, so we know then this integral, the evaluation of that integral is going to be 0, hence that's my expected value. All right, part B. First of all, differentiate this. You got two functions multiplied, so therefore we're going to have to differentiate it. Of course, with respect to z, using the product rule. So this is like u, and this is like v component. So derivative of z is 1, and times v plus z, that's u, times v prime. So this itself, that's v, but here this is a composite function. So you're going to have to use the chain rule. So the derivative of the power, which is minus z, and times that original exponential function. So if you tidy all that up, then you get that. Okay. So now I'm going to make this term the subject, because in the question, go back to the question here, you were told that you're going to have to integrate that. Okay. All right. So here, what that means is you're going to have to integrate this one. So therefore, it's sensible that I make this guy subject first. So then I get this. Okay. So that term goes over there, and this term now goes comes over here. So now integrate both sides with respect to z and then evaluate from negative infinity to infinity. So then I get this. So integral, integral, and this one here, interesting thing happens. If you differentiate and then integrate, what happens? You get back to where you started with. So you get this function back. So that's that one. And also on top of that, you're going to have to evaluate it. So that's all integral, integral. And this one, because you're getting back to where you started with, you don't even have to integrate. So that's just this. And then evaluate it from negative infinity to infinity. Now, why does that become 0? Well, let's rewrite this. So this is a negative power. So if you rewrite it, so that's going to be z e to the minus half z squared. So that's z over e to the half z squared. Now, watch what happens. So this is an exponential function. This is a linear function. So as z gets bigger and bigger, whether it's positive or negative number, this is always going to be a positive index. So the rate of growth for the exponential always outbeats the linear. So as z gets bigger and bigger, this outpaces that one. So what does that become eventually? Where as x gets positive infinity or negative infinity, the whole thing becomes 0 because the denominator gets large very fast. Okay, so it's going to overwhelm the numerator. So the whole fraction is going to be 0 as z goes to whether it's a positive infinity or the negative infinity. So the whole thing is going to be 0. And then I just now have to evaluate this. But the actual question is asking you to evaluate not this, but that times 1 on root 2 pi. Okay, so what that means is I'm going to have to multiply every single term by 1 on root 2 pi. So that's that one. And then notice I'm pushing it back inside. And why? Because later on, it'll become apparent why I did that. And this one we know is 0. So 0 times a constant 1 on root 2 pi still 0. So that's that one. And now this by definition is phi z. Okay, why? Because let's come back up here. So let's see. Okay, so that's phi. 1 on root 2 pi times e to the half, negative half z squared, which is this. Okay, 1 on root 2 pi e to the minus half z squared. Now also, by definition, you've given that a PDF function, so that's going to be just 1. Okay, so the evaluation of that, which you're asked to do, is just 1. Okay, now, and we are going to have to use this result to do part C. Okay, so the variance, first of all, it's the expected value of z squared minus square of the expected value. So it's now z squared times 1 on root. So that whole thing, remember that was the phi z, the frequency function. And we just figured out that the expected value is 0. So that term, we don't have to worry about that anymore. Now, again, I'm taking that out, then you get this. But from part B, what do we just do? We just proved that this integral is 1. And that's basically what we got up to here. So that's that one. And we know from part B, then, okay, so this is 1. Hence, the variance is just 1. Okay. All right, so that about does it for this short video. And that actually concludes our section on the continuous random variable. So the next section that I'm looking at is going to be just pure extension 1 content, and that is on vectors. All right, so I'll see you guys next time.